Okay, so welcome everybody to our second round of the Algebra, Particles, and Quantum Theory seminar series. I'm pleased to introduce to you tonight's speaker, Anna Pachol. Anna was recently promoted to Senior Lecturer in Mathematics at Queen Mary University in London, where just this last year she won the Science and Engineering Faculty Award for Equality, Diversity, and Inclusion. This is following another prize that she won the year before, the Learning Resources Champion Award. After completing her PhD at the University of Wrocław in Poland, Anna went on to postdoctoral positions in similarly scenic locations, starting first with the Science Institute at the University of Iceland. Later, she took up the position of Junior Principal Investigator for a Marie Curie Fellowship, which she held in Torino, Italy. After this, she won a Marie Curie Individual Fellowship at Queen Mary University of London. And it's there that she eventually accepted the role of Senior Lecturer in Mathematics. Anna has an impressive repertoire of research interests, including quantum groups, non-commutative spacetimes, deformed relativistic symmetries, gravity, and non-commutative differential geometry. Over the last few years, she's worked together with Sean Majid on a project called Digital Quantum Geometry, which is a framework of quantum geometry constructed using zeros and ones. So this is what she's going to be telling us about today. Now, before we begin, I'd like to emphasize that everybody that showed up today is here to learn. So I would hope that everyone feels comfortable enough to raise their hand and ask a question throughout the talk if they have one. If you accidentally ask a silly question, of course, it's not a big deal. You just brush yourself off and try again next time. So I would especially like to encourage questions from graduate students, upper level undergraduates, and postdocs. So Anna, the floor is yours.
Okay, thank you very much. So yeah, first of all, thank you also, Cohl, for invitation. It's really great to spread the digital quantum geometries all around. So, and of course, yeah, I'm happy to answer any questions at any point of the talk. So please do stop me in case something is unclear. So firstly, I will give you a little bit of motivation, because I realized digital quantum geometry probably sounds a little bit strange. So my motivation comes from quantum gravity. So the search for quantum gravity, where we know continuum differential geometry cannot be the mathematical description once we want to consider quantum and gravitational effects at the same time. So we have to look at some kind of intermediate step before we actually know the full theory of quantum gravity to be able to see what kind of properties we may be dealing with. And here this quantum geometry comes to play. And of course, in many different approaches to quantum gravity, different things are meant behind the quantum geometry name. So I particularly will be focusing on the non-commutative geometry approach. So here in this talk, we will be using this framework of non-commutative geometry as the non-commutative Riemannian geometry, to be more precise, because we still want to have some kind of resemblance of the curved spaces. So we want to use the framework of Riemannian geometry, but now we want to know what the quantum version of such geometry could look like. And here, just to underline that the non-commutative differential geometry is already more general than the classical differential geometry, even if our algebras will be commutative, but it's enough to actually just require that the functions and differentials do not commute. And here, this is quite interesting because we can keep the algebra classical, commutative, but it's enough to have already much more general picture, just thanks to non-commutativity of functions and differentials themselves. So this is kind of the starting setup, and the plan of the talk is as follows. So firstly, I want to introduce the quantum Riemannian geometry framework. So this is quite the general framework. Now it has been a lot of research has been devoted to this already, and then only then I will specify what digital is. So then this second part of the talk will be on actual digital quantum geometry and some results in this area. So To start, how do we build up the non-commutative differential geometry? Where so usually in differential geometry, in the ordinary differential geometry, we start with a manifold and algebra of functions. Here, we completely forget about any manifolds or any spaces, actually. We just need to have some starting algebra. And here for the later applications, for example, to quantum gravity, we call this starting algebra coordinate algebra. But bear in mind that since there may not be any manifold or any space behind here, this coordinate name is just a name. So it's really just an abstract algebra. You can use here any algebra you like. And then to have some kind of differential structure, so we want to replace the usual differentials by some kind of non-commutative differential structure. And here for this, we need to define a space of one forms, which will be suitable for that algebra we have chosen in the first step. And here we have to define the differential bimodule omega-1 with the with differential map, which would be still obeying the Leibniz rule, but we would not need this condition to be satisfied anymore. So here, this classical condition where the functions commute with one forms is being replaced by something more general here. So this no longer has to be satisfied. And why do we require the bimodule? Because we need to be able to multiply the elements from our coordinate algebra from the left and the right, to multiply the one forms by the elements from the algebra from left and right. So that's just this requirement comes from there.
So, can I interrupt? So if H bar were to be introduced at some point, is it here that it would be introduced in the non-commutativity of H or of F and DG?
Yeah, exactly. Yes. So here, what is quantum Riemannian geometry? So quantum differentials are basically what I just told you. So here I will come back to this in a more proper definition, but then we can be starting from that, we can build up all the elements we have in Riemannian geometry, like metric, Levi-Civita connections, curvature, and so on and so on. But now generalizing it to this more algebraic picture, which is this non-commutative picture from the beginning. So here, let me give you a proper definition of this differential calculus. So this is our first order differential calculus. And remember here, the algebra can be any abstract algebra over any field. It could be commutative or non-commutative. And this definition just gives you a way of defining some differential structure on that algebra. So here, omega-1 is just the set of one forms, which has to be the bimodule. Then we need to have a linear map, which is satisfying the Leibniz rule. And we also need to have this surjectivity condition, which basically means that these one forms are generating the whole omega-1. There is another condition, which is optional. So this is called connectedness condition, but it's not always satisfied. And in the classical case, it's corresponding to the connected manifold. So here it may happen that it's not satisfied, so that's why it's not a requirement. So I think perhaps this is pretty standard, but please do ask any questions if something is unclear. And with that, to discuss higher order forms, or the analog of the higher order forms, we introduced the differential graded algebra. So we build we still use the derivative which can satisfy graded Leibniz rule, and here we have this exterior product if the surjectivity condition is satisfied. If not, this is just a associative multiplication. So this is just a wedge product, which is the associative multiplication in this algebra. So here, this is how we build up from the first order to higher orders this differential forms. For the applications of what I'm going to talk about today, it's enough that we just get to omega-2, and that's it. So we will not need much higher forms than just 2 tensors. So this is basically the setup, which is already much more general than the classical geometry, as I said, because even if we take the algebra being commutative, there is this requirement of the functions not commuting with the differentials. So this is already giving us a little bit more general description than classical differential geometry. And then how do we define quantum metrics on such algebra, on such coordinate algebras? Well, so then once we have the first order differential calculus defined, the metric will be just an element from omega-1 tensor omega-1. And here all the tensor products will be over the algebra. So here general metric will be just an element of such tensor product. And we have some conditions which should be satisfied. So here we require this quantum symmetricity, where the wedge on this metric is 0. And also we require invertibility. And this invertibility is in the sense of existence of such a bimodule map here, which would be the inverse metric, like analog of the inverse metric, such that this condition is satisfied. So it looks a little bit more complicated, but if one writes it on the components, it looks exactly what the inverse metric would look like. So here, this condition in this framework actually leads to the requirement that such a metric, such an object defined here, which will be invertible, meaning satisfying this condition, actually turns out to be that it has to be central in the algebra A as well. So here, this commutator of G with the elements from the algebra have to be 0. So this means it's central in this algebra. And here, just to make things a little bit more familiar, I chose a basis in this algebra A, in the coordinate algebra A, as x mu, which are just generators of that algebra, so that I can show you the general form of the quantum metric, which you can recognize as something we usually write in the classical differential geometry as well. So here, this looks completely familiar, I hope, but we have these additional requirements which come from this setup. So here, this quantum symmetricity, invertibility, and then invertibility leading to centrality of such a metric, which may seem to be quite restrictive, but as we will see later on, it actually still gives us a lot of, it gives us quite a rich moduli of examples. So these are the quantum metrics. Then we have also quantum connections.
Can I ask a question about your metrics, if you don't mind?
Yes.
So this, what is this G mu nu? Is it valued? What is it valued in?
Yeah. So here it's in the algebra A.
Okay. So is it possible? So do you have a? Can you define dimension? Is there a notion of dimension or signature, for example, in this more general?
So here, so I will be showing you some specific examples where all these things will be clear. For now, A could be finite or infinite. So here, this could be anything. If this is a finite algebra, then here this would be a specific dimension. So let's say, for example, n-dimensional algebra A. With coefficients G mu nu being valued in that algebra as well. And here you can have signature as specific coefficients, as the sign of the specific coefficient. So it's like a little bit more put as a additional condition if you want a specific signature. Okay. So yeah.
Can you get things like indefinite signatures?
I think so. I'm not sure how it would exactly look right away, but I think so. I think it's because it just relates to the putting additional condition on the additional restrictions on this G mu nu coefficients.
Okay, thank you.
Yeah. So here moving on to quantum connections. So again, we have to define everything in terms of this abstract maps, and here the bimodule connection will be such a map from omega 1 to omega 1 tensor omega 1, which is firstly left connection. So here it has to know what happens when the elements from our coordinate algebra A multiply the forms, one forms from the left. So this is the left connection prescription. And if we require it to be bimodule connection, it has to additionally satisfy this condition here. So it has to know what happens when the elements from the algebra, from the coordinate algebra, multiply one from the right as well. And for this, it has to be satisfied for some sigma. And it does look like it's some kind of additional requirement, but it's actually not, because if the connection is bimodule connection, then there is a unique sigma associated with that connection. So it's actually not additional data required here, because it will be uniquely determined. Sigma will be uniquely determined. And here also, perhaps for physicists in the audience, if you are more used to of using the connection along the vector fields, so this will look a little bit different, but it's actually the same if you think of it as a bimodule connection, as a map along the vector field. But you can think of it exactly the same as this map here, where this first tensor product will be evaluated against the vector field. So here you could think of it as a connection along the vector field V, where it's a map from omega 1, because this already got evaluated against that vector field. So here, this is a more abstract way of writing things, and also very common for non-commutative geometry approach, where often the framework is given without vector fields, without using vector fields at all. So here there have been many authors using this type of connections as well since quite a while. And how to extend such a connection to tensor products? Well, it's just very natural prescription how to do that, and this is how we will do it. Why do we need to extend it to tensor products? Well, because we want to know what happens, for example, when the connection acts on the metric, right? So here, the metric is the tensor product in omega 1 tensor omega 1. And for example, if it happens that nabla on G on the metric is 0, then we call such a connection metric compatible. So that's in complete analogy to what we know from the usual differential geometry as well. So we want to keep all those requirements as well here. Also, we can define the torsion if we can extend omega 1 to extend to omega 2. Then the torsion will be defined like this. So here it's just a wedge product on the connection on omega minus d omega. And if we have a connection which is metric compatible, meaning this condition is satisfied, and additionally it's torsion free, meaning this whole thing is equal to 0, then we call such a connection quantum Levi-Civita connection, because again, in analogy to the usual differential geometry. Additionally, we can define curvature as well in a similar way. So again, this will be given by this form here. So I have prepared a quick. Okay, sorry, not yet, but in a moment I will give you example of how to write down all these maps for the usual case of the functions on a manifold. So you will see all these maps actually reduced to something familiar right away. But before that, let me just give you the two more definitions. So here we also will need the Ricci tensor, and here, well, it's given as this map here. And this is where actually we need some additional data, because we need this lifting map I here. So here, this is the first time where some kind of ambiguity enters the whole approach, because this lifting bimodule map will need to be chosen or added by hand in a way. So we know how to do it in, of course, in the classical case, it's unique, but in this non-commutative case, it's no longer unique. So here, this is the first ambiguity. But once we do that, once we define this Ricci tensor up to this lifting bimodule map I, then we can go on and define what is the Ricci scalar, which will be just this inverse metric acting on that tensor. And for the Einstein tensor, we can consider either the usual definition. So here, just Ricci minus 1/2 S times G. Alternatively, since our framework is defined over any algebra, any abstract algebra over any field, this 1/2 here would not really go through for any field. So field independent option would require putting some other coefficient alpha here. And this, of course, could be coming from the theory. So it could be related with the quantum dimension, for example, as it was suggested in this reference here. But it should be field independent in principle if we want our theory to be valid for any abstract algebra. And here for all this, so all I have just spoken about, there have been last year, I think, published this book. So this is summary of everything and much more. Of course, the book is quite big. So here, Edwin Bex and Sean Majid have summarized everything they've been working on within this quantum Riemannian geometry approach. So if you feel like you would like to know a little bit more and get to know a little much more examples, I think that's a really good reference for that. But now let me just give you this classical case example, which perhaps makes things a bit more clear. So if I just go back to taking a smooth Riemannian manifold and algebra of functions, and our omega 1 will be just the usual one forms with the basis forms denoted as dx mu, then the metric will be looking exactly like this. So here we could think of some specific metric, for example, as well. And this already commutes with the functions from A, because by definition there is no this non-commutativity in the classical case. So this commutator of the metric with any function from A will be just 0, because we can move this function through the whole each of the elements. Then with the linear connection, we use the Christoffel symbols, right? So here this is written in terms of Christoffel symbols, and it is bimodule connection also because there is no this issue of multiplying by elements from the left or right because they commute. So here, if I just use these two elements and want to see how the torsion, for example, looks like, I just plug in the connection. So the one which was just written in the previous slide, I just plug it in here. This is 0 because that's the d squared, and then I get the usual coefficients for the torsion. And if I want my metric, my connection to be torsion free, we get this antisymmetricity of the Christoffel symbols in the lower two indices. So here, this exactly reduces to what we know from the classical geometry, and also for the curvature, doing exactly the same. So here I'm just using the definition of the connection by plugging it in explicitly with the Christoffel symbols. And then, of course, I have to do a little bit longer calculation, so I skip that here. But you can see that exactly this will give us the Riemann tensor coefficients in terms of the derivatives of the Christoffel symbols and so on and so on. So this really reduces to what we know. And now for the Ricci, since there was this lifting map here, we in the classical case, we actually know what this lifting map will be, because this is exactly the wedge product being written as an antisymmetric version of this tensor product here. So here, in non-commutative case, this does not work because we don't know what antisymmetricity means in the non-commutative geometry. So for example, we cannot use this map as this option always as a default option. There may be cases when this is possible to be used as well, but it not as a default prescription. So here again, doing the whole calculation by using the Riemann curvature from the previous slide, plugging it in and doing a little bit longer calculation, I get exactly the usual Ricci tensor, which exactly is known from the classical case. So as you can see, this abstract maps gives us exactly what we want in the classical case, but the benefit is that they actually work over any abstract algebra, over any field. So it is really much more general formalism. And now moving on to the digital case, unless there are questions, perhaps I will give maybe a few seconds.
What about non-associative algebras?
Oh yeah, that's very interesting. I think there are some examples considered with non-associative algebras. Although, yeah, I wouldn't know maybe the reference right away, but I think I've seen some attempts of, yeah. But yeah, they are much more difficult
yes.
to deal with, yes.
Keeping track of brackets.
I think I would have to look it up, but I think I've seen somewhere attempt of applying this framework to non-associative algebras as well. Okay, so moving on to the digital. So the digital quantum geometry. Well, so recalling that this framework of quantum Riemannian geometry works over any algebra for any field, we could take, for example, field Fp, or what we did, we actually focused on something much more calculable, so F2 with zeros and ones. Well, first of all, because we wanted something which would be easy to investigate, and actually, so we could classify all the possibilities. But on the other hand, it was already enough to get quite a rich structure as well. So, of course, the idea would be to generalize and look at other fields as well, in principle. So here we chose the finite field as an idea of discretization scheme. So coming back to physics, or approaches from physics, where by some kind of discrete approximations we can make systems more calculable, or just to find out a way to investigate more general theory by looking at some kind of toy models. And this was our idea here as well. And of course, even being interested in the theory over the complex numbers, it's good to know what happens on the simpler cases as well, especially if we don't know how the general theory may look like in the case of quantum gravity, or even in the case of quantum Riemannian geometry over the complex numbers. If you recall, this condition for the quantum Levi-Civita connection is actually non-linear, so it's not easy to calculate or solve for any metric, even as it is. So that's why we just went with the field of zeros and ones. And surprisingly, we actually got quite interesting results. So let me tell you about them.
Do you mind if I ask you one more question about your previous slide? So have you looked at all at somehow starting with F2 and then taking some sort of a continuum limit?
No, because yeah, so ideally one should also look maybe at F3 and F4, but what we have seen actually, ability of classifying everything already over F2 was quite demanding, I would say, because, well, some part of this work was done over computer, so in Mathematica and in R, and this already was taking quite a lot of time. So going even to F3, I think I would have to change the method completely and try some different programs, because this was already running quite long. So then, yeah, having an idea for some kind of, continuous limit would require having a look at a few more of the basic examples first.
Okay.
But yeah, definitely good. Good question. Okay, so here, so what we actually did, so in this series of works, we firstly tried to classify all the possible coordinate algebras up to dimension 4 over such field. So here, just to know how many of the unital associative algebras are there in such a framework, then we were looking at building up this quantum Riemannian geometries in each of the cases up to 3 dimensions, and this was already getting quite complicated. So we couldn't go to 4th dimension here. And then lastly, we were also looking at the quantum group. So where, if there are any Hopf algebras associated with the algebras we found. So here, I will mainly focus on building up these digital quantum geometries, but if I have time, I will also mention a little bit about the quantum groups as well. So how do we set up the whole thing? Well, we start with the coordinate algebra as a unital associative algebra over F2. So here my basis will be denoted by x mu, and I will be starting with x0 being just 1. And here, so here this will be for this low dimensions. And we write the product in the algebra in terms of the structure constants. So now, from now on, all the structure constants are in the either zeros or ones. So as you can see, this will be allowing us for a lot of simplifications along the way already. And we have classified all such algebras. So what are they? Well, in one-dimensional case, there is only one such algebra, of course, which is 1 squared equals 1. For 2 dimensions, there are three inequivalent commutative algebras, which we firstly denoted A, B, C, but then we actually found out what they were. So here are their real names with the products as follows. So here we have x1 squared equals 0, x1 squared equal x1, and here x1 squared equal 1 plus x1. So in 3 dimensions, we had 6 commutative algebras and 1 non-commutative one. And for 4 dimensions, there were much more, of course, there were 16 commutative ones and 9 non-commutative ones. So the idea was to build up quantum Riemannian geometries on each of them. So, and classify how many there are. For this talk, I will spare you the details, and I will only focus on one case from 3 dimensions. So here, I will, well, okay, I have a summary. So here I have, for first dimension, for one-dimensional case, there is only the one option, of course. So there is no metric because the derivative on 1 is 0. So that's nothing else. For 2 dimensions, actually, we had the central metric, which turned out to be never quantum symmetric. So this condition with the wedge product on the metric giving 0 was never satisfied. And only one metric which looked like this was admitting quantum Levi-Civita connection, which was equal to 0. So again, not very interesting cases here. However, moving to 3 dimensions, we already had a lot of interesting geometries here, and actually, surprisingly, many of them were not flat already here. So we considered all of the algebras, and also we considered 2 cases of the differential calculi. So first, we considered the 1-dimensional omega-1, and then 2-dimensional omega-1. So here I will focus on this 2-dimensional omega-1 case, which is the universal differential calculus. So here, this is what the rest of my talk will be about. And to keep things simple, I also choose the basis for this omega-1. So we have 2-dimensional case where omega-1 is just dx1 and omega-2 will be dx2. So this will just make things a little bit simpler in the description. And I choose one case, one example for this group algebra F2Z3, which firstly we denoted as algebra D. And I will keep that notation in some of the slides because it's just a bit looking better, while the formulas are looking a little bit better when I just keep this D name. So here we have the three-dimensional unital commutative algebra with the basis as x1, x1, and x2 with the explicitly written relations here. Then we find what is the corresponding universal differential calculus, and it has these relations here. Later we found out that we realized that this algebra is isomorphic to this group algebra, so we could actually just use the 1, z, and z squared as generators of this algebra instead. So here, this is our setup, and how the quantum metric looks on this algebra. So out of algebra, we just follow the formalism, and everything comes out from the formalism. So here we just define a general metric as an invertible element looking like this, where now, so Gij with the two indices are the functions from my algebra. But I can, since it's this algebra, this specific algebra, I can write it in terms of the structure constants G mu ij, which will be just zeros and ones, and this basis in this algebra. So here it can be written in either of the ways, and then I need to require it to be quantum symmetric. So the wedge product on G should be 0, and also I need to require this invertibility condition, which means this metric has to be central in that algebra. And these conditions give us specific form of the quantum metric. So here it is determined up to this functional parameter beta. So here there are no other possibilities for this case. And beta, so beta can be from the algebra. And to be able to calculate the connections, I just need to take the special cases of this functional parameter here. So beta can be 1, z, or z squared as the generators from the algebra D here. And what it turns out from the calculation is that there are 12 quantum Levi-Civita connections associated with 4 associated with each of these cases, but 9 of them turn out not to be flat. So thinking about the what we are actually doing here, just taking this commutative unital algebra and getting not flat case in terms of non-zero Riemann curvature, it seems really, really interesting. So we were quite surprised by this result also, and this seems to be really related to this non-commutativity only, this non-commutativity condition, which in this kind of interpretation would be kind of quantum case. So how do these connections look? Well, we have to calculate a little bit more. So here I write this connection in terms of the structure constants against 0 and 1 here. And the sigma, this map, which is the one which we require for the connection to be bimodule, also can be written in terms of the structure constants, which are zeros and ones. Taking that, we can rewrite the curvature also in terms of this structure constants, where I take this vol as the basis of the omega-2. So here I just express it as an element from omega-2 tensor omega-1 in this way, in terms of the basis elements. So here, this is how it looks in general. Well, remembering that the structure constants everywhere are these zeros and ones. So here the calculation can be done explicitly. So what we looked for is the metrics to be quantum symmetric. So this we already had, but for the quantum Levi-Civita connections, we wanted to have metric compatibility and torsion freeness as well. So we imposed these two conditions and see what comes out from the calculation. So here, for each of the betas, I give you like a list. I will not discuss it in detail. Of course, it's just to show you that one can get this connections, these elements explicitly calculated. But for beta equal to 1, for that metric here, we are getting connection, one of the connections looking like this, and the curvature tensors associated to this connection look like that. So first example of not flat connection, and here there are 3 more. One of them it turns out to be flat, but the 2 next ones are having non-zero curvature tensor here and here. So of course, yeah, I will not go into more details on that, but as you can see, using this framework of digital quantum geometry, one can explicitly calculate everything in this theory. And there are further 4 quantum Trivita connections for this B functional parameter being the Z, and another for the Z squared. So here plugging in the metric here. So this is of course all in the paper if you are curious how actually they look. But what we wanted to do next is to investigate what happens with the Ricci and Einstein tensors. So here the definition I gave you before will require this lifting map. So what do we do for this lifting map? Well, again, we can assume a form written in this way, where these coefficients ij would be from the algebra. So again, I could write them down in terms of the structure constants and the basis from the algebra as well. But we need to require that the wedge on I will give us the basis element from omega 2. So this is the condition we need to satisfy. And then what is in this case, the I still is not unique. So it actually turns out for the case of this algebra D, this group algebra F2Z3, that we can add any functional multiple of the metric to the whole map. So here I wrote it explicitly. So this would be, this comes out from the calculation plus this general term gamma times G, where gamma could be any function from the algebra. So in this way, this gives us kind of three parameter description of this lifting map. So clearly it's not unique. However, we can look at some kind of cases, specific cases, which may resemble the classical differential geometry. So for example, if we want to look at Ricci being quantum symmetric, then I can get some specific cases for the gammas. So here for these gamma parameters, and here it's just a summary of what I just told you. So here we have the metric with beta equal to 1. So these 4 connections I showed you explicitly. Then one of them was flat. For this one, of course, the Ricci is also flat. But for the 3 remaining ones which were not flat, they were all different. It turns out that the Ricci tensor actually is all the same. So here, for all 3 of them, the Ricci tensor is given by this formula here. The Ricci scalar then ends up being this. And if Ricci is required to be quantum symmetric also, so having kind of the same symmetry as the metric, then it reduces to this case where gamma 1 and gamma 2 are given by these numbers here. So there are some restrictions we can impose on this lifting map, but there is this additional condition, for example, of quantum symmetricity we require. And then for the remaining two cases, it's a very similar way how it looks. However, for the third one, it turns out that the Ricci tensor is never quantum symmetric. So that's what happens for this algebra. And here if we associate this notion of quantum dimension to this whole picture, just to see if we can see why certain things happen like as they are, then maybe there is some kind of explanation for this last case. So quantum dimension is defined as this inverse metric on the metric here. in our case, it will be either 0 or and 1. And we see that in this last case, the actual quantum dimension is 0. So perhaps that's why this Ricci tensor is never quantum symmetric in this case, where in the first two cases, the quantum dimension is equal to 1. So perhaps that's the reason. For the Einstein tensor, we use the definition, which is Ricci plus S times G. So here, remember, there was this factor -1/2 in the classical case, which we cannot use. But from our field, we either have 0 or 1. So we chose 1 here. So that was one of the possibilities. And here we also get the whole list of cases, and we can look at the specific cases, because again we have this ambiguity for the gammas. So, for example, if Einstein tensor is not 0, then we can look for the choices of gammas when the nabla on Einstein would be 0. So here, this nabla on Einstein, so connection on Einstein would be applying the connection in the element of omega 1, tensor omega 1. So the same as on the metric, and then contracting the first two factors with the inverse metric. So here, this is how this formula would work out in this case of quantum Riemannian geometry. And once we have that, we can look at the specific constraints for this lifting map, which was parameterized by the three parameters of gamma cases. And again, summary in the table. So for the metric, which was with this beta equal to 1. We had the 4 connections. One of them was flat, so Einstein is also equal to 0, Einstein tensor. But in other 3 cases, Einstein tensor is equal to this. If Ricci is quantum symmetric, Einstein turns out to be 0. So here, this is also nice result, because it seems to be quite compatible with the classical case, let's say, in a way, what we would expect from the classical case. And this nabla on Einstein here is the result for gamma 1 equals 0. This would be 0 as well. And then for the second case, quite similarly. And again, the third case, which is a bit strange, because there is Ricci never quantum symmetric, we get another option for Einstein as well. So here, yeah, so this is the main summary for this particular algebra. But what we did is, so yeah, here I can just maybe briefly go through that case. So what we find is 3 metrics. Well, no, it's a 1 metric which is parameterized by the beta, which can take which we split into 3 different cases. And for each metric, 1 connection is Ricci flat for all the lifts, and it's actually flat. That's where the curvature was 0. But other 3 connections all have the same Riemann and Ricci curvatures. And then when we choose the Ricci to be quantum symmetric, so in the same symmetry as the metric, which means in our case the choice of this lifting map, and in other words, choice of the gamma i's, then Einstein tensor turns out to be equal 0. Otherwise, we can also choose the lifting map so that the nabla on Einstein is equal to 0. So here, this is just a summary of what I already told you from the tables. And moving to other algebras, what we find is in 2 other cases. So for this algebra we called B, but which was actually an algebra of functions on a group, and then algebra which we called F, which was actually F8. We find similar results, so we can actually classify all these results, and it is done in the paper if you are curious how they look, because it's again a huge list of the quantum Levi-Civita connections, Riemann curvatures, and so on and so on. So this was possible to be done for these 2 algebras. The other algebras, they had no invertible central metrics, so we did not find anything interesting here. And in the paper, we also investigated the properties of the geometric Laplacians as well. So here I would like to also mention a bit about the quantum groups, but not sure if there are any questions to this already. So just to, maybe just to summarize, but if there are any questions, please go ahead in the meantime. So this approach gave us quite a rich landscape of quantum geometries already for the low dimensions. So as you have seen, we already found, even for one algebra, which I showed you explicitly, we already found some interesting results, which were not all of them were flat. And moving to other two algebras, it's quite similar. Some are flat, some are not flat, and it was possible to build up this digital quantum geometries in this way. However, for the 3 dimensions, it seems that the interesting cases only are when we take the commutative algebra. So we investigated the one non-commutative case as well, but actually it didn't have interesting quantum geometry in 3 dimensions at least. So here just quite a summary of what I already said. So in each case, we were able to find a unique calculus and unique quantum metric. And when quantum metric was admitting quantum Levi-Civita connection, we have a digital quantum Riemannian geometry in that case. So we actually got the whole moduli of such quantum Riemannian geometries. And there was a proposition of the Einstein tensor as well, but I do admit this is quite ambiguous, considering that there is no really a generalization to abstract algebra over any field, Einstein tensor, yet. So here we just tried this as a one option. Perhaps there is a better way to define this as well. And well, so maybe let me just skip this last part. So here you've seen in the tables quite explicitly what was happening for each of the metrics for this algebra, group algebra F2Z3. And just as a very quick teaser, I think I have perhaps like 2 minutes still. So since it was possible to do this full classification of quantum Riemannian geometries in these cases, we also got curious what will happen with the quantum groups, because when talking about non-commutative geometry, one often remembers also about quantum symmetries as well, which are described in the language of Hopf algebras. So actually, we were also able to completely classify all Hopf algebras and the B algebras up to 4 dimensions over this field F2. And for 3 dimensions, so since you already heard a lot about the 3-dimensional case, it turned out that only the algebra B and D, the one I discussed in detail, admit Hopf algebra structure. So here, this turned out to be the only case where the Hopf algebra structure exists. However, the remaining algebras in 3 dimensions were admitting many B algebras. So here, here we can actually put it all on a graph. So if I take the relation where A to B means that algebra A admits a B algebra structure which with coalgebra, which is isomorphic to the dual of B. So I know it's a mouthful, but it's just about kind of matching the two. So if I can match them in this way, then this D and B algebras are related with each other as Hopf algebras, where the remaining ones are related with the as B algebras, where the B algebra turns out to be the coalgebra of that B algebra turns out to be isomorphic to the one which it points to. And here for the 4 dimensions, we were able to do the same for all 16 commutative and 9 non-commutative algebras. For Hopf algebras, we got this relation. We denoted them here in the letters of alphabet. So A to P for commutative ones, and then NA and to NI as non-commutative ones. So for Hopf algebras, we get this picture. And for bi-algebras, we get quite much more complicated picture because it's much more richer structure. So here, if quantum groups are your topic, I do invite you to have a look on this paper as well, and perhaps maybe get in touch with me if you are interested to hear more about this. So yes, with that, let me just conclude. I hope using this finite fields is actually a quite nice toy model. So I'm hoping to investigate a little bit more cases to see how they work out, maybe a little bit more complicated ones. But it does allow us, as we have seen, this finite field does allow us to test the certain definitions and see all the elements explicitly, which is perhaps a good thing to have some explicit ideas. And well, coming back to the quantum gravity motivation, since quantum gravity is usually seen as a weighted sum over all possible metrics, perhaps this could lead us to the way of defining quantum gravity as a kind of weighted sum over all possible such quantum geometries if we consider the field, for example, FP instead of just F2. So that's all. Thank you very much for your attention. And well, if there are any questions, I'm happy to answer.
Well, thank you very much, Anna, for a great talk. Does anybody have any questions? Okay, so Alex Klein, I'm going to unmute you. Okay, yes, go ahead.
Good afternoon. I have a question. In quantum mechanics, energy has some spectrum. So therefore, the same should apply to tensor energy momentum and therefore to curvature and connection. How it's reflected in your geometry, this?
Well, you mean tensor, energy momentum tensor?
Yeah, because I have multiple connections, so it's maybe not unique trajectory, and therefore some kind of should somehow reflect geometry itself.
Yeah, so here, thank you. That's a very good question. So for since all this relation, for example, with Einstein tensor, it's not exactly coming from geometry, but from algebra. There is no really an analog of the tensor, energy momentum tensor here, because it's one would have to have a generalization of the energy momentum tensor over algebra first, right? To add to this picture. But as far as I know, this is not uniquely described in the framework over any algebra over any field.
I see. And another question, what about uncertainty principle?
Oh yeah, okay, so thank you. That's a very good question. So coming back to the maybe beginning of my talk. So here, since in this framework, in these particular examples I showed you, my algebras actually turned out to be commutative. The uncertainty principle would look exactly as in the quantum mechanics, because the coordinates, the x nu would commute. So here, the non-linear uncertainty would be between the coordinates and momenta. However, the picture does allow, so this framework does allow for studying the algebras which are non-commutative. So this coordinate algebras, A in general, where the coordinates themselves may not commute. And then one would have to consider uncertainty principle also for coordinates themselves, right? So this would be an addition to the uncertainty principle between coordinates and momenta. So that there would be an additional uncertainty principle in the picture. But for what I've been discussing, since my algebras turn out to be all the interesting cases were all commutative algebras, here the quantum mechanics would just have this one uncertainty principle between coordinate and momentum.
Mm-hmm. And the last question is about differential, because what exactly on this page, or even in quaternion algebra, this equality would look a little different, because if F is the map, then is differential is tensor product. So it's a little, it cannot be equality. You really cannot they interchange by their places.
Okay, so here you mean when there would be tensor product between f and
The J should be tensor product, yeah.
Yeah, okay, so yes, but for example, okay, thank you, yes, that's a good question also. But what I mean here is that classically what happens, yeah, this is here, for example, this last element in this commutator, dx nu times f, this would be just a normal multiplication. And by commutativity, I mean that I can move this f in front of the dx. So this is not a tensor product, right? So here it's just a normal multiplication where I can just move f here in front of this dx nu, for example.
What this point does mean? This is product.
Yes. So it's a So omega 1, it's a bimodule, which means I can multiply one forms by the functions from either left or right with the usual multiplication, right? So here, this is not a tensor product in this case, yeah.
I see, thank you.
I'm not sure if I...
It's okay. Does anybody else have any questions? Okay. Okay, so Torsten, please go ahead.
Okay, yeah, my question is more fundamental. Okay, you choose some non-commutative differential structure or some algebra, which can we see now, but how did you choose it? First, I thought you maybe you may have in mind that to directly choose a quantum geometry without any quantization procedure, but later you speak about that you have to be in contact with quantum mechanics and choosing the functions like that. How did you, but at the end you have to make a choice, and how did you do it? What is the principle behind to make a choice on a non-commutative differential structure?
So yeah, thank you. So here our choice, all our choice is only in the coordinate algebra. So the starting point is to choose coordinate algebra, and then from that everything follows. So for example, the differential structure follows immediately from that choice of that algebra. So for example, in the case I've been describing for this specific algebra D, once I choose the algebra here as this group algebra, I know the relations. So the algebra is described by this specific relations. And if I want to have the universal differential calculus, this is uniquely determined. So because I have to require this bimodule, I have to require this derivative satisfying the Leibniz rule, and I need to require this surjectivity condition.
Okay, but how did you choose the coordinate algebra?
So here, in general, in non-commutative geometry approach, where one starts with the so-called quantum spaces or quantum space-times, you choose the algebra you want to study. So for example, you may be familiar with the Kappa-Minkowski space-time or with Moyal-Weil space-time as well. So one could choose the algebra A, the coordinate algebra, as one of those. But here, for example, what we did, we actually classified all the possible ones. So we asked a more general question, because our question was how many there are of all possible ones. So we were just looking for all possible algebras, which were unital and associative in the specific dimension. So for us, it was just, these are all the possible options, and we were investigating each of the options individually.
And the hope is if you sum over all such algebras, you get a substitute for the sum over all matrix in a path integral.
Well, like that. So yeah, that could be one idea, for example. Yes, exactly. So for 3 dimensions, for example, we know that there are only these 3 algebras, 3 unital associative algebras over F2. There are no more.
Okay, So the beginning is a non-commutative coordinate algebra. Okay, I see. Otherwise, maybe a comment on non-commutative geometry. There's also many other possibilities to have a choice for a non-commutative algebra or a non-commutative geometry, like, for instance, very complicated foliations, and then you have the space of leaves of the foliation is also a non-commutative geometry. So you can, that's maybe only a comment on that.
Okay,
thanks a lot. Okay.
Cohl, you are muted. I think you.
Right.
Okay, so first unmute myself and then see what's happening here. So, okay, let's see. Okay, so I'm going to do that. All right, so Nosrat, I'm going to.
Thank you for the nice talk. Maybe my question is not directly related to your works. There is an approach in canonical general relativity. They use the graph in the space-time, and they start from the Hamiltonian approach to the general relativity, discretizing the Hamiltonian, and they have some, for example, Ricci, discretized Ricci, and Riemannian scalar, or something like this. Is there any relation between this study and those approaches?
Well, so I'm not sure I heard because there was a little bit of interruption, I think. So I think you were asking about the Hamiltonian approach.
Some canonical Hamiltonian approach. They also discretize Hamiltonian approach for the general relativity, Einstein, Hilbert, and Hamiltonian, and they have some form of discretizing curvature, for example, Oliver or Forman-Ricci curvature. And in the quantumium, they have obtained the general relativity, but they have some similar results to you, but they don't have non-commutativity. They have only discrete space-time, discrete graph in the space-time. Exactly.
Yeah. So I think I know now better. Thank you. So in a way, this is a discretization, but in kind of orthogonal direction. So this digital quantum geometries approach, it's a little bit different than just considering discretized space or lattices, because here because usually those, like maybe the framework you are talking about, it's still considered over the complex numbers. Right, so usually, even for discretized spaces, people usually consider frameworks over the complex numbers, where here we kind of go in an orthogonal direction because we take the field finite, which is proposing a bit different type of discretization than the one which is maybe more commonly used. So I'm not sure if that answers your question.
Oh, thank you. Thank you so much.
Okay, next question, Andras. I'm going to unmute you. There you go. Go ahead.
Yeah, so
Andras?
sorry. So I just would like to ask, if you go to your first slide, well, I am not very familiar with the whole framework, but that was quite clear. So if you start, if your prototype, let's say, is ordinary differential geometry, when your algebra is the function algebra, this is, of course, not finite dimensional, but it is a topological one. Yeah, so it has a nuclear Fresher topology with the standard topology. And if you want to demonstrate the whole machinery on this particular example, do you need to refer to the topology or not? So it's...
Yeah, thank you. That's a very good question. So actually not, because you can actually forget about any spaces whatsoever. So here you can only talk about the algebras. And of course, in non-commutative geometry, there are certain theorems which can give you back the topology if you want from some non-commutative cases. But in this framework here, in principle, you don't need to refer at all to any manifold or any space. So you don't have to refer to any topology if you don't want to.
That's rather surprising.
Well, because you can think of it as just building an algebraic framework. So algebraic differential geometry analog, but your algebra could be really anything. So so it does not have to always refer to some space, right? So it does not have to be coming from some specific manifold, for example.
I mean, if you want to reconstruct, for example, ordinary differential geometry, so you say that you can simply forget about the algebra, about the topological data of the function algebra.
Yes. So in non-commutative geometry, yes. So in principle, you can just base everything on the algebras. Yeah.
Thanks.
Okay, a question from Jose. Go ahead, Jose.
Hello. My question, since I'm an outsider from these algebraic approaches, more to try to understand if you can address things like, for example, people that do image processing in a computer, they end up doing something about geometry with only zeros and ones.
Yes.
Could it be somehow related to your approach? That's the question.
Yes, so thank you very much. So actually, that was kind of our idea where we were coming from. So our idea was to see if some of this would be relevant to some kind of quantum information or anything dealing with zeros and ones. So for example, what we did consider in the first paper I mentioned, when we did the classification of all the possible algebras, we considered how to embed the products of those algebras as electronic gates. So if you're interested in that, I would definitely recommend you having a look on this electronic gates there. But in principle, so here, in this first paper, here in principle, I'm not sure yet. There would be some specific application of this, because our idea was that maybe if somebody would know how to apply certain things of this approach in some kind of quantum computing, but unfortunately this was beyond my my knowledge of the topic here. But definitely this was the original idea that perhaps some of this could be related to this other framework. Yeah.
Thank you.
Okay, question from Carlos. Just get that. Oh, see what happened here. It did not work. Oh, there we go.
Thank you. So now that we're in the applications part, so related to the first question, maybe momentum operators in Hamiltonian lattices, in lattice Hamiltonians, so that can be casted into algebras such as Pauli matrices. Do you have a specific example on those, or not yet, or is on the way?
Oh, okay. So thank you. So actually, so this I think would be maybe not so easy to formulate in the algebraic framework completely, because, well, in principle, the momenta should be some kind of dual elements to the coordinates. Yes. So we haven't looked at this, but definitely that's a very interesting.
But it doesn't need to be dual. It needs to be differentiable, right? So you don't need actual dual space. It's just a trick for old school physicists, right? So yes, you just need to have it from the discrete to the smooth, So maybe this helps in a way to have everything in simple space, so to speak.
Unfortunately, I don't have a good answer to this, but definitely that's interesting, interesting thing to think about. Yeah.
Thank you.
Okay, so I'm just going to take a look here at people that have their hands up. So Alex, your hand is up. Did you have another question? I'll just unmute you here. Alex?
Okay. Just this was not down.
Oh, okay. Fair enough. Okay, no problem. Okay, and so Jose, did you have another question? I'll try to unmute you here. Jose? No, I think he...
No.
Okay, fair enough. Okay, but Torsten, you have another question, so let me unmute you. Okay, there you go. Please go ahead.
Okay, thanks. Another question. At the end, if you choose a quantum geometry, you have to be in contact with classical geometry. So I miss a little bit some kind of free parameter, like a Planck's constant, to get in touch, or where you can choose to be zero and then get in touch with classical space-time. First question. Second question, in non-commutative geometry, as far as I remember, one has also a spectral triple where you choose a Dirac operator instead of a metric. Is it also possible to make such a thing in your approach?
Yes, so okay, first question. If you would like to see the parameter coming from quantum gravity, for example, so like let's say Planck length, or yes, it would have to enter in the
in that place.
Yeah,
okay, I see.
Yes. So
okay.
I've been not writing it, but you are right.
Yeah.
So here the non-commutativity is only between the one forms and the elements from the algebra. So all these relations would have this parameter. Okay. So and then if you take a limit of that parameter, it would reduce to the classical case.
Okay. Yeah, I see.
And the second question, yes, thank you also very much for this spectral triple case, because I wanted to mention it. So actually, when building this first order differential calculus, so basically this is where the two approaches split in a way. So the Cohn approach now bases on the Dirac operator, and out of the Dirac operator and spectral triples, they are building up this whole structure from that point. So this is the last common point, let's say, of the two approaches. Where
I see. Okay.
Yeah, and in this case here, one can just towards this quantum metrics and so on and so on. But this is completely parallel to the
analogs. Okay. I see now. Thanks a lot. And so thanks for the nice talk.
You're welcome. Thank you.
So it looks like Jorge has a question, so I'm just going to unmute you here. Please go ahead, Jorge.
Okay. Yes, thank you very much for the very nice talk. And I just want to know whether you have something that could be defined as functional derivatives or functional integration over these structures. Is it
yes, I know there is something, yes, along this line, but unfortunately, I don't know from top of my head how this would work out. But I think, yeah, in the reference in the book of Bex and Majid, I think they may be commenting on this. Yes, so in this book here, I think there may be something mentioned like this.
Okay, thank you very much.
Okay, thank you again, Anna, for a wonderful talk. This might be a good place to close things off. So thank you very much.
Thank you.
And thank you to everybody for so many really great questions. So I should just say to close off, in 2 weeks' time, we have our next speaker, who is Shadi Talvidarzadeh from the mathematics department at Rutgers University. And for quite a while now, I've been curious about this interpretation of quantum theory known as Bohmian mechanics. It's been hard not to notice that out of my friends in the quantum foundations community, the ones who have turned towards Bohmian mechanics really seem to fall head over heels for it. So when Shadi speaks in a couple of weeks from now, I hope he'll elucidate for us what it is exactly that Bohmian mechanics has that other interpretations don't. So thank you again, Anna, for a wonderful talk, and hopefully we'll see everybody again in 2 weeks' time.